record, so we are recording, right? Yeah, okay, so hope you guys had a good spring break, whatever it was you did, whether you worked, whether you played, whether you did a little bit of both, whatever it happened to be, but I hope you guys had a good break. Let's see. What we are doing today is I'm going to cover two sections, y'all. They're kind of short sections, so we should have time to do both of them. Today we're going to go over 4.2 and 4.4. That homework y'all will be due by next Monday at the end of the day. And then Wednesday we will go over 4.5, okay? And again, I'll upload the videos to our playlist, on YouTube or whatever. But let's see, I already went ahead and I accessed the notes of 4.2 and 4.4, and I put them here in my OneNote. So let me get my pen going. There we go. Okay, so 4.2, y'all, talks about these things called linear approximations, differentials. So we're going to talk about linear approximations to a function at a point. We're going to write the linearization of a given function. We're going to draw a graph that illustrates the use of differentials to approximate change in a quantity. And we actually don't do the relative error or percentage error, at least not in the homework problems, okay? So, okay, linearization, y'all, is basically just the tangent line at a particular point, okay? So it says, given a function y equals f of x, the tangent line at x equals a is the line that just touches the curve at the point a and f of a with the slope m equals f prime of a, right? So every time we said, can we find the slope of the tangent line, we would take the derivative and then we would evaluate it at a particular value. So it says, we can think of the tangent line equation as itself as this right here. The tangent line is f of a plus f prime of a times x minus a. All right, so linear approximation says for values near a, the tangent line can be used to approximate the function f of x. What we're saying here, y'all, is that, again, this is what we call linear approximation, right? So we are approximating, right? We're not finding exact values. Hello. We're not finding exact values, but we are approximating. What we're saying is that if we were to zoom in on this thing right here, we're saying that in this kind of little window right here that we have, that the tangent line here behaves very closely to the function itself. Okay, that's in essence what we're saying, is that the tangent line behaves very much like the function itself. Okay, it's not exact. Again, it's not supposed to be exact. It's supposed to be an approximation. Okay, and so that's one of the things that we're going to be doing here in 4.2. Okay, it's basically we're finding just the equation of the tangent line and we're using it to approximate values of the function. Okay, so let me kind of zoom out a little bit because there's something I want to copy down right here. There we go. That's what I want to copy down. So my linearization is going to be f of a plus f prime at a times x minus a. Okay, so I'm just writing that same formula right there, guys, but it's just like finding the equation of the tangent line, okay? So nothing too out of the ordinary here. Times x minus a, right? And remember what we did before. Remember, that's the slope of my line, right? That f prime of a is the slope of my line. So again, all we're really doing here, y'all, we're just using the slope-intercept form or the point-slope form of the line. This is just another way of writing it, okay? Yes? Okay. So take a look at the first problem we have here. It says f of x is 2x squared minus 6x plus 5. We want to first find f prime at 4. Okay, so let's do that first. Let's first find the derivative, okay? So y'all, let's go ahead again. I know we've been off for a week or so, but let's see if we remember how to find the derivative of 2x squared minus 6x plus 5. What's the derivative of 2x squared? 4x. The derivative of a minus 6x is just a minus 6, and the derivative of 5 is 0, right? Okay, so look, there's the derivative of our function. We now want to evaluate this at 4. So we're going to now find f prime at 4. So that's 4 times 4 minus 6. So 16 minus 6, everyone agreed? 10? Okay. So here we go. We got 10. Okay. Now, what we're going to do is we're going to find the equation of the linear approximation. Okay, so the first thing we need to do, y'all, since we are evaluating this at 4, we need to find the value of f of 4. Okay. So look, I'm going to use my calculator here because it's going to be pretty easy to do this on my calculator. I'm going to clear all this business. Okay, my y equals, I'm going to go ahead and enter this in, 2x squared minus 6x plus 5. There you go, enter. Okay, let me put this. Let's go to bars. Let's go to y bars. Let's go to our function. The first one, and again, we're evaluating this at 4. So at 4, we have 13. Okay, so f of 4 is, excuse me, is 13, right? So notice, this is how we're going to write the equation of our line, y'all. It says f of a. Well, we just found f of a to be what number? So we're going to write 13 plus f prime at a. We just found f prime at a to be what value? 10. And then in parentheses, x minus that particular value what we're evaluating it at. Okay, x minus 4. Now, I know, guys, we could distribute, we could do all that kind of stuff. I'm just going to leave this part as it is. Okay. Now, it says use the linear approximation to approximate f of 4.4. And it says compute the actual value of L of 4.4. So what I want to do here, if this is my L of x, my linearization, I want to find L of 4.4. So that would just be 13 plus 10. Notice what value we're plugging in now. 4.4 minus 4. Okay. So look, I'm going to do this on my calculator. First question, what is 4.4 minus 4? 0.4. So we're going to take 0.4, we're going to multiply it by what value? By 10. Okay. And then we're going to add what number to it? So we add 13 to it. John says we get 17. Okay. So what we've done here, y'all, is we have done an approximation. We didn't find the actual value of f of 4.4, but we found the linearization of it. So we found we use the equation of the tangent line to find the value of 4.4, and that should be really close to the function evaluated at that value. So now look at the second part. The second part says, can we actually compute the value of 4.4? Yeah, we can. Remember, this is my original function, right? So I'm going to come back to my calculator. Where is it? Here we go. Okay, I'm going to go to my bars. I'm going to go to my function. I'm going to do my first one. And I'm going to enter in 4.4. And look at the value that I'm coming up with, 17.32. Again, what do? We found an approximation. This is the actual value. So are we close? Yeah, we're pretty close, right? And again, that's the whole point of linearization. The linearization is just saying, we're going to find the equation of the tangent line. And if we were to take values close to that tangent line at that particular point, like in this case, close to 4, we should be getting something very close to the actual value of the function, because the tangent line and the graph almost mimic each other when we're kind of very close to it, right? So I'm going to kind of scroll back over here, y'all. So remember what I said when we scroll in here. Again, look at the blue graph. The blue is the actual function. The kind of yellowish line is the tangent line. You can see that they're really close. They almost overlap, right? There's a lot of points there that are really close to each other. That's what linearization basically says. That if you're in this, guys, those of you, I know Jennifer is going to be a math major, so at some point, Jennifer is probably going to hear this term. Some of you guys may hear it too, the more advanced math courses you take. But they talk about something called a neighborhood. So anytime you take values that are really close in that neighborhood, and what I mean by that neighborhood are values really close to, yeah, whatever that value is there. So close to A. And again, when we mean close to A, we're talking about, you know, within maybe a tenth or something like that, or a couple of tenths. You know what I mean? If I'm thinking about the value 3, is 7 close to 3? No, we're talking about like 3.1, 3.2, 2.9, 2.8, stuff like that, right? Or 3.001 or 2.999, stuff like that. That's in essence, that's what linearization basically is, okay? So, y'all, for these problems, this is what we're going to be doing. We're going to be finding the equation of the tangent line. We're going to evaluate it at a particular value, and we're going to be getting approximation. Okay, so here's my next problem. It says, use linear approximation, in other words, the tangent line, to approximate the square root of 36.1 as follows. Let f of x equals the square root of x. Find the equation of the tangent line f of x at x equals 36. Okay, so the first thing we're going to do, y equals, guys, can I write the square root of x as x to the power of 1/2? Okay, so that's my y. Does anybody know what my y prime would look like? 1/2, right? And then x to what power? Excellent. Man, you guys are doing great. Even after spring break, you still remember how to do this. It's good, guys. Okay, so look, y'all, the only thing I'm going to do here, I'm going to fix that power to the negative 1/2, and I'm going to bring it down to the bottom. Can I write it like this? Since we said power of 1/2 means the square root, and since the exponent is negative, doesn't that mean that that guy is just going to come downstairs now? Okay, now, the next thing I want to do, y'all, we're going to evaluate it at 36, okay? Because it tells me, let's evaluate this thing at 36. Okay, so look, we're going to come back over here, 1 over 2, square root of 36, 1 over 2. The square root of 36 is 6. And 1 over 2 times 6, everyone agree, is 1/12? Okay, so first thing we're going to do, y'all, we're going to find the linearization, okay? In order for me to find the linearization, I also need one other value. I need to find, from the original function, I need to find f of 36. So I want you to notice something. If f of x is equal to the square root of x, what is the square root of 36? 6. Okay, so the way we write the linearization is going to be f of a plus f prime at a times x minus a. Okay. So f of a, y'all, was just the number 6. So I'm going to write that right here, 6. Plus f prime at a. Hey, look, we found f prime at a. We took the derivative and we ended up with 1 over 12. And then x minus, what was the value we were plugging in for x? 36, right? This is what our linearization looks like. Okay. Now, we're going to, using this, we're going to find our approximation for the square root of 36.1. So what we're going to do now, y'all, we're going to find L of 36.1. So if this is my L of x, all I'm going to do is everywhere I have an x, I'm going to plug in a what? I'm sorry? That's right. I am finding the approximation for the square root of 36.1. Because that's what we're doing now. That's how we find the approximation. We're going to plug in 36.1 into here. And not the square root, because what are we finding, John? Remember, we're finding an approximation, right? So we're finding the approximation using the linearization, right? Does that make sense? So the function is actually the square root of 36, right? Or the square root of x. Instead of us taking the square root of 36.1, we're going to plug 36.1 into here. Better? Excellent. Everybody agree that 36.1 minus 36 is just a 0.1? Okay, so look, y'all, on my calculator, first thing I'm going to do, 0.1 times 1 over 12. Okay, and I'm coming up with 0.08 or 0.008 with a whole bunch of threes, and I still need to add 6 to that, and so I'm coming up with 6.008 with a bunch of threes. There we go, right? So look, this is the approximation that we got using the linearization, right? So, yo, if we wanted to find the approximation using the function itself, what we could do is we could say, what is the square root of 36.1? And I want you to notice, look at the value that we come up with here. 6.00832. Do you see how close we are? We're really close, right? Again, that's the whole point of linearization, right? So if you think about what we've been doing so far, y'all, we've been finding the equations of tangent lines, right? We're still finding the equation of the tangent line, and then we're just evaluating it at values really close to that particular value of A. And what the linearization says is that what we're coming up with when we plug this into our tangent line, we're coming up with almost the same thing as if we had evaluated the function at that point. Okay. Yes. Why is it that yeah. I mean, yeah, you can write it. You can, so look at the directions. Note for this part, give your answer to at least 9 significant figures or use an expression. So you could have written it as a fraction if you wanted to. It gave me options, didn't it? Yeah. So it said use this way or that way. I chose one way. Okay, so look, we got another problem here. We're going to go about this all the same way. Using linear approximation, i.e. the tangent line, to approximate 1 over 0.502 as follows. Let f of x be 1 over x. Find the equation of the tangent line to f of x at a quote-unquote nice point near 0.502. Then use this to approximate 1 over 0.502. Okay, so first thing I'm going to do, y'all, here, y is equal to, can I write 1 over x as x to the power negative 1? Okay, so if that's my y, does anybody know what my y prime is going to end up being? Negative 1x or negative x? What power now? Negative 2. Very good. Excellent. Okay, y'all, can we write it like this? With positive exponents, can we write it as negative 1 over x squared? So again, remember, the negative 1 is right here. If I have an x to the power negative 2, we can bring it downstairs. The power becomes positive, right? Okay, so look what we're going to do now. It says we want to find the equation of f of x at a nice point near 0.0502. So I'm looking for a nice point here, y'all. How about if we pick x to be 0.5? Because that's really close to 0.502, right? So look, if I find y prime of 0.5, that's going to be negative 1.5 being squared. So yeah, negative 1 over a 0.25. Okay, so I am going to use my calculator here, y'all, because I'm curious, what is negative 1 divided by 0.25? Negative 4, right? Okay, cool. So we got a nice pretty value. So this here is equal to negative 4. Okay. So y'all, the other thing I'm going to do is this. If that's my x value, I want to find f of 0.5. So that'd be 1 divided by 0.5. Anybody know what's 1 divided by 0.5? 2. Good. Excellent. Okay. Now we're going to write our linearization. The linearization goes like this, y'all. f of 0.5 plus f prime at 0.5 times x minus 0.5. Okay. So f of 0.5, y'all just told me was 2. F prime at 0.5, we found that to be negative 4 times x minus 0.5. And I'm going to do this. I'm not going to write the plus minus. I'm just going to leave it as a minus. Okay, now to answer the question, what we're going to do is we're going to plug in 0.502. So we're going to find L of 0.502 equal to 2 minus 4, 0.502 minus 0.5. Okay. So again, here on my calculator, y'all, the first thing I'm going to do is I'm going to enter in 0.502 minus 0.5. John tells me 0.002, right? And then we got to multiply that number by what? Negative 4? Okay, so I'm coming up with that. And then what are we going to do with that 2? What's the sign of the 2? Addition. So we're going to add 2 to that now. Okay. And I'm coming up with 1.992. Okay. Now, that's the approximation that we got, right? We did our linearization. That's the approximation that we got. I'm just curious, y'all, to compare it to the actual value. If we were to take 1 divided by 0.502, look at the actual value, right? 1.992 with some other changes behind it, right? So again, linearization just means, can we find approximations of particular values using linearization? Guys, sometimes linearization, I think, is a good technique. Sometimes not so much. Like in this particular problem, like, can I do it? Yeah, but why? Because it's so easy to take my calculator and divide 1 point.
I think this is important.
Probably, it probably is. Uh-huh.
Division is like a lot longer for computers to process division than multiplication for calculation.
So there you go, right? So there's uses, and guys, for the most part, these approximations work really, really well, right? Sometimes they do, sometimes they don't. There's actually a problem that we're going to do in a little bit. It might even be the next. No, it's not this one. This is a pretty easy, breezy cover girl problem. But it might be the one after this. There's one I was doing, and I kept checking my work when I was at home because I was like, this just doesn't seem right. And it is. It's just when we do the linearization, it's just not a good example of linearization. Like it just doesn't approximate it very well. So again, you can see with like this problem here, when we did the comparison, hey, we were really close. When we did the comparison here, we were really close. For the most part, we're really, really close, right? Because again, when I come back and I think about this picture right here, right, we're in that little neighborhood and we're getting values that are really, really close. And sometimes, yeah, it works out great. And there's other times when just deviating a little bit, either to the left or the right of that value A, whatever that value A happens to be, the function, if it's a very steep function, it changes so much. You know what I mean? So I'll show you guys in a minute what I mean by that. But yeah, there's a problem here that we're going to do in a little bit, y'all. Let me zoom out. And we'll get to that one in a little bit. But let's go ahead and continue with, here we go, this one here. So I just want to, I'm doing these problems, y'all, because they're part of the homework, right? It says, let f of x equals the square root of x. Find x close to 24.99 for you know the exact values of both f of x and f prime of x. Then enter those exact values. Okay, so look, what value would be really close to 24.99? 25. Okay, so if f of x is equal to the square root of x, what would f of 25 be equal to? That's right. So right here, y'all, we're going to put a 25, and that answers fine, right, for the function itself. Now, I do want you to take a look at the second part. The second part actually has f prime of x. Okay, so remember what we did earlier, y'all? We said f of x with the square root, didn't we say that was the power of 1/2? Do y'all remember what the derivative was when we took the derivative of x to the power 1/2? We can work it out. I'm just curious. Very good. 1/2 x to the power negative 1 John, can I like this? Can I write it as 1 over 2 square root of x? Okay, good. So now, y'all, we're going to do the same thing. We're going to find f prime of 25. Okay. So this is 1 over 2 times the square root of 25. So this is 1 over the square root of 25 is 5. Wouldn't that just be 1/10? So right here, y'all, I'm going to plug in a 25. And right here, I'm going to plug in a 1/10. Y'all, when you're doing your homework this evening or next Monday night or whenever it happens to be, right? Anytime between them, um, you're going to have a problem very similar. You know, they may not give you 24.99. What other perfect squares do you know? Like the square root of what? 36, square root of 4, right? Square root of 9. You see what I mean? So they might tell you, say they were, and say it was instead of, right now we use the square root of 25, right? Because we're taking numbers close to 24.99. So they may give you something like 8.99. Why? Because I know 8.99 is really close to 9 and the square root of 9 is 3, right? Or they might give you something like 3.99. Why? Because 3.99 is very close to 4 and we know the square root of 4 is 2, right? Stuff like that, okay? Let's see. Here we go. Okay, here's another one. This one, y'all, we're going to find the linearization just like we did before. So, y'all, one thing I want you to notice about this problem here on the directions, it says find the linear approximation of f of x equals cosine of x at c equals pi over 6, and then round the coefficients to 4 decimal places. So I am going to use approximations here, okay? I am going to use decimals. All right. So let's give this a shot. Let's see. First thing I need to do is I want to find f of pi over 6, which would be cosine of pi over 6. And y'all, because I am doing approximations here, I'm not even going to use my chart. I'm just going to make sure that I'm in radians. Yes, I am. So what's the cosine of pi over 6? Cosine of pi over 6, I'm going to go to 4 decimal places, y'all, is a 0.8660. Okay. All right. The next thing we need to do, we need to find f prime of x. Okay. Anyone remember the derivative of a cosine x? Very good, y'all. Negative sine x. Perfect. Okay. So now I'm going to find f prime, excuse me, of pi over 6. So this is a negative sine of pi over 6. So let's try that. Negative sine of pi over 6. Isn't that a negative 1/2? Yep, negative 1/2. Okay. All right. So now, y'all, we're going to fill in the blanks. Remember how we write the linearization? The linearization says we're going to have f of a plus f prime at a times x minus a. Okay. So first part, f of a. Hey, f of a was f of pi over 6, which we came up with a 0.8660. 0.8660. Okay. Plus the derivative at a. What was the derivative at a? Negative 0.5. So let me change that. Instead of a plus, let me put a minus 0.5 x minus. Now, y'all, I'm going to leave it as pi over 6 right here, but you could take your calculator and divide it out. I know it told me to go to 4 decimal places. I just don't feel like taking pi divided by 6. You know, there's a linear approximation.
And if it's not a problem, it's the entire number of actions like that,
Well, no, because remember, it's not. So number one, it's not going to tell you that it's wrong. But if it doesn't take it, just convert that to decimal, right? Because what does it say? Go to 4 decimal places. Right? All right. Okay, so the next thing we have here, y'all, increments and differentials. We can finally say what dy and dx mean. Okay, so it says in this figure, the value of x changes from a uh, by delta x to a plus delta x. Okay, so if this was my value of a, this is the change in x, right? So delta means change, right? So this value here would be a plus delta x, okay? And the resulting change in y of equals f of x is the change in y. So what we mean by this, y'all, here is if I were to look at this particular point here, and I'm going to call it a plus delta x and f of a plus delta x. So the way we find the change in y is we take the difference in those particular values right here. That's why they're calling it delta y, right? Delta just means change, okay? Differentials, dx and dy, are the changes in the x and y coordinates of the tangent line. So in the tangent line, delta x and dx are actually the same because I'm still changing it by that particular amount. But the dy, y'all, the dy is the change in the y values of the tangent line, okay? All right, so that's what the little dy means. The way we find dy, y'all, the way we find dy is going to be f prime of a times d of x. That's the particular point that they're giving us. Yes, the first point. Okay. So let's take a look here. It says, find the differential dy when x equals 1 and dx is equal to 0.04. Okay, so the way I'm going to find dy, y'all, we're going to find f prime at a times whatever our value dx is. Okay. So look, here's my original function. Okay. The way we're going to find the change in the tangent line is we have to take the derivative of this function here. Does anyone remember what is the derivative of the tangent function? Anybody remember the derivative of tangent? Secant squared. Yeah. So secant squared of 4x plus 7. What else do I need to do? Anybody know? There's one more thing, y'all. I'm missing one more part. The inside. Very good. These, remember the chain rule, y'all. So we got to do the derivative of the inside. What's the derivative of 4x plus 7? 4. Okay. No, because look, dy, f prime at a. We just found the derivative, right? Okay, times dx. Okay. So look, y'all, what we're going to do now, we're going to evaluate this when x is equal to what value? When x is equal to 1 and dx is 0.04. So look, this is what we're going to do. Secant squared. Remember, we're plugging in x equals 1. So 4 times 1 plus 7, 11, times 4, and my dx value is a 0.4. Okay. So y'all, on my calculator, because my calculator doesn't have a secant squared button, couldn't I write this as a 1 over cosine squared of 11? And then 4 times 0.4 should be something like 1.6? They both mean the same thing. They both mean the same thing. Okay, so look, y'all, when I'm doing this on my calculator, the first thing I'm going to do, because 4 times 0.4 gave me 1.6, I'm going to go 1.6. Let me pronounce it. There we go. 1.6, okay, divided by the, and actually I'm going to do some parentheses here. Insert parentheses, cosine of 11, close that off, square it, okay, and I'm going to hit enter, and I'm probably going to come up with a really massive number. John, did you come up with the same thing? Yep, 81,000. I'm sorry? But you came up with about 81,687? Yeah. So look, y'all, right here, we're coming up with 81,687 point, what was it? Point, yeah, let's go 0.7. We're okay leaving it like that. 81,687.7. That looks very messy. Let me just say. Okay. Now, y'all, we're going to do this problem again, except now we're going to change the value of dx to 0.08. Okay. So look, my dy is going to be equal to, so I'm going to write out this. I'm going to write secant squared of 11 and 4 times 0.8. So 4 times 0.8 should be something like 3.2, and then the rest of the bottom stays the same. Secant squared of 11. Okay. So look, let me do this part of my calculator, y'all. The only thing I'm going to change when I do this on my calculator, instead of a 1.6, I'm going to change that 1.6 to a what? 3.2? Right? Okay, and let's hit enter. And John, did you come up with the same thing? 163, 375. Jennifer, are you coming up with the same thing? I thought I heard you. That's why I was asking.
Oh,
Okay,
no,
just
I wasn't.
okay. I just wanted to make sure that you're good here, Jennifer. Point something, 0.3, right? Okay. So remember, y'all. Remember what we were finding here, right? We were finding that change in the y value for the tangent line, right? That's what we were finding, right? We found the change of the values in the tangent line. I want you to think about this for a second, okay? So where we had in this particular function, what we had in this particular example, the x value that we were given x to be 1. And look how much we changed. We only changed by a 0.4. So the difference between here and here was 0.4. That would make this value 1.4, right? So we didn't change a whole lot, right? We went from 1 to 1.4. What we found was the change in the tangent line, right? Not the change in the actual function, but the change in the tangent line. Remember we said the tangent line, for the most part, is very similar to the function itself when we're really close to that initial value that they gave us, right? So it's the change in the, no, it's not necessarily the change in the slope. It's the, well, it is the slope of the tangent line between those two particular values, right? Okay, what I want you to think about now, y'all, is if we were to find the actual change in the y, okay? So what I want you to think about for a second is, remember what our function was? Our function was y equals, what was it, tangent of 4x plus 7, right? I want you to do this for me, y'all. Could you all do me a favor? Could you help me find y of 1? Wouldn't that just be the tangent of what value? Wouldn't it be the tangent of 11? Okay. What do you come up with when you do the tangent of 11? Negative 225 point, I'm sorry, how much? 951. Okay, we're going to do this one more time, John. We're going to find y of 1.4. So remember, if I'm going to find y of 1.4, I got to take the tangent of 4 times 1.4 plus 7. So 4 times 1.4 should be 5.6 plus 7. Isn't that really the tangent of 12.6? Okay, so what's the tangent of 12.6? 0.033642. If we were to take this value here and subtract that value, do you think we would end up with 81,687.7? Not at all, right? Y'all, question. Do you remember what the tangent graph looked like? You may not. I know it's been a little while. The tangent graph does something like this, right? Tangent graph does something like this. And so if you notice, y'all, between right here, this is pi over 4. Between this value and this value, do you see how that graph takes off? And it takes off really, really, really high, right? And does anybody remember what these things were called? Asymptotes, right? So vertical asymptotes, right? So guys, remember what happens? The graph gets really, really close to that line, but it never touches it. But I want you to think about, as I get to values close to here, like suppose I pick this value and I just move a hair over, do you see how much change there is right there, right? There's a lot of change in the y values, right? So that's why the differential, is it good? Yes, it is. Does it always work? Not always. Why? Because when we get close to those horizontal asymptotes, things like that happen, right? Things like that happen, okay? I'm sorry, say that again? Well, we don't, periodic is what you're referring to, where they keep kind of repeating over and over again. Well, we want to kind of, they're going to be good, John, except around vertical asymptotes. They won't be good around vertical asymptotes because as we get closer to those, remember, those lines shoot up really, really high. Or on the other side, they're coming down really, really steeply, right? Okay, so look, we got a little bit more to do here. We're going to do one where hopefully we're going to compare the two values, y'all, and they're hopefully going to be, close to each other. So, right, so look at this one here. It says, let y equals 3x squared. Find the change in y. We're looking for delta y. So we're not going to do the derivative just yet. When x equals 4 and when delta x equals 0.3. So again, let me give you an example of what it is we're looking at here, y'all. 3x squared does something like this, okay? It has another part too, but we're now looking at when x equals 4. So here's x equals 4, and then we're going to move a little bit of a distance of 0.3 so that this value would be 4.3. And what we're going to do is we're going to say, okay, what's this value? What's this value? We're going to find the actual change in the y, okay? Yeah, we'll talk about that April, but yes, it is. Okay, so look, y'all, let's see if we can figure out what's going on here. So first thing I want to do, I want to find y of 4.3. Okay. So this is 3 times 4.3 squared. Okay, let me get my calculator, let me turn it on, let me clear all this mess. 3 times 4.3 being squared, and I'm coming up with 55.47. Okay. And then I want to find y of 4. That should give me 48, because 4 squared is 16. 3 times 16 is 40. And now we're going to find the difference between those two. So minus 48, what is it, like 7.47. That's the actual distance between those two values, okay? Now, we're going to find the differential, which is going to be the change in the tangent line, y'all, okay? So look, there's my tangent line. So the way we find dy is we're going to take f prime at that particular value times dx, okay? So first, let's take the derivative. The derivative of 3x squared, everyone agree, is a 6x times whatever my value of dx is going to be, right? Okay. So what value are we plugging in for x here, y'all? 4? So 6 times 4 times a 0.3. Okay. So 6 times 4 is 24. 24 times 0.3, 7.2. That is the change in the y values of the tangent line between those two things. So again, you can see here the differential and the actual change in the y values are pretty close to each other. 7.47, 7.2, we're pretty close, right? But again, when we have those kind of equations that have asymptotes, yeah, it just doesn't work out as well. What do you think? Did we do okay with 4.2? Did it make sense? Don, am I doing all right? Yeah? Steve, is this working? Yeah? All right, so I'm going to check to see who else is with us online real quick. Let's see, go back this way. Let's come over here. Oh, we got a few folks here. Let's see, Angela, Jennifer, Mattia. So we doing okay with these problems, y'all?
We're good, sir.
We're good? Okay,
Yes.
just checking, y'all. Okay, just checking, guys, just checking. Okay, so look, y'all, that is 4.2. We're gonna do 4.4, but what I want us to do real quick, y'all, let's take a little 10-minute break. So I'm gonna stop recording this.